Continuing a new example here. So this one is an inclined surface. So the previous ones were on a flat surface where we could see that normal force and gravity were perpendicular to displacement. But this one here is an incline. And one of the things we're going to see here, if you have an inclined surface, then gravity is doing work actually because it's not perpendicular to displacement anymore. But let's read the question and solve it. 5-kilogram package slides 2.8 meters down along a ramp that is inclined at 24 degrees below the horizontal. The coefficient of kinetic friction between the package and the ramp is, that's a mu k, so let's say that's a mu k, 0.310. Okay. So then we're going to calculate the work done on the package by friction, work done by gravity, work done by normal force, then the total work done on the package. And if the total work done is non-zero, that means now we know that what happens here, object will change its kinetic energy, using this net work, right? Or total work is equals to delta K. Remember, if this is not zero, means your kinetic energy will change. So we're given that if the package has a speed of 2.2 meters per second at the top of the ramp, what is its speed after it has slid 2.8 meters down the ramp? Well, the 2.2 meters per second is the initial speed, which we can use to find initial kinetic energy. Now will it change or not, then will depend on the total work done. If the total work done is zero, you have the same speed. If the total work done is non-zero, then your speed will change, and how it will change will be more than less, depends on this. Remember, if work done is positive, that means delta K here is positive, means V final greater than V initial. If work done is negative, total work done, right? Then delta K here is negative, means V final is less than V initial, you slow down. All right, so we're gonna look at this example. We're gonna calculate each work done. We're gonna calculate the net work, and then we can figure out, what we should get. We should get higher or less, depending on just that, and then go ahead and calculate it. All right, so let's start. I'm giving myself more room over here. So let's say here's my incline. All right, so this is my incline, angle theta. Okay, let's do this. So I'm going to use theta for the angle between force displacement vectors. So here for the incline, I'm going to use alpha. Alpha just another letter that we're using for the angle. All right, so here's what I have. This is my incline, and this is my package. So it's going to go from this here, this initial point, right? So from this initial position to this final position. Okay. And then, I'm going to calculate. So again, you can use, initial final, you can use 1 and 2, you can use A and B. I think in the solution, I have 1 and 2. So let's just go ahead and actually use that. So let's say this is 0.1. Let's say this is 0.2. All right, so I'm going to do package as a particle. And what I have here, you can see, right, I'm going to do a coordinate system. Because one of the things I need to do here is I need to show you guys that this is being y-axis, this is the x-axis. How are some of the things related to one another? Okay. So what I have here is, it's a surface with friction. So that means there are not only normal force acting on the package, here's the normal force, not only gravity acting at this angle, right? Alpha over there, right? So this is gravitational force. But there's also a friction which is acting in this direction, opposite to the motion, right? So this is an F of K. So I have those three forces acting on it. And if I do a force table, again, I will tell you in a minute why. Let's say I need this force table. So you can see, right, these are forces, X component, Y component. So you can see that in terms of then, I have a normal force, I have gravitational force, and I have the kinetic friction. Okay. So let's look at normal force. Well, normal force is acting in a positive y direction. It's a simple one. Well, the gravitational force, if you remember, right, for the incline, if I take this gravitational force and I break it down into components, so what I will have here is this. So this is then the y component, and this is the X component, which is just this guy over here, right? So you can see that in a way, the gravitational force has a mg sine of theta, sine of alpha as a X component. Again, I'm using alpha for the incline angle, and the X component of the gravity is, remember, mg times sine of incline angle, so it becomes mg sine of alpha. Then the Y component will be mg cosine of alpha. Since this is fourth quadrant, this is positive, this is negative. Okay. Then what I have here is the kinetic friction, which is in a negative X direction. There's no Y component, right? And remember, so technically then my system will be accelerating in X direction, but will be at will not have any net force in the Y direction, because you can see, right, as the package is sliding down an incline, there's no acceleration in the Y direction, because I take the X direction or X axis to be along the the ramp axis. All right, so remember, we get two equations from here. That in the X direction, I'm going to get f of k, or let's say here I get mg sine of alpha minus f of k equals mass times horizontal acceleration. Equation 2, normal force minus mg cosine of alpha equals 0. That means normal force is equals to mg cosine of alpha. Again, this is not 2, this is alpha. Let me kind of make that a little more obvious. All right, so the reason I had to go through these steps is to get this guy. And I will explain you in a minute why I need that guy over there. All right, so let's see what happened then. Again, this is the Newtonian dynamics, and this is useful for some of the things that we are doing in this example. But then from here, I'm going to look at all, the energy approach. And technically, if you already knew this, you don't have to do the steps. So let's say if I'm solving this problem, I'm not going to do the steps, because the only reason I needed to do the steps is to know what the normal force is, which is mg cosine of alpha. That's what I needed to get out of that. Because when I'm looking at this, problem from the energy point of view, what I have here is I have point 1 over there, and I'm going from point 1 to point 2, and that, doing this displacement, and here's the displacement. Doing this displacement, right, there are 3 forces acting on it. All right, so here's my, net or total work done. Work done by the gravitational force, plus work done by normal force, then plus work done by the kinetic friction. Because I have, you can see right in my free body diagram, I have 3 forces. So I just write down in terms of that. Well, what is the work done by the gravitational force? Well, its magnitude, mg, times the displacement, delta x, then times cosine of theta between gravitational force, not the component, but the gravitational force, and then the displacement vector. That's why I have this guy here as theta. You can see, right? That's the theta, because I'm talking about cosine of theta from gravity to displacement, that angle. All right, then plus, then here I have normal force times displacement, then times cosine of basically the angle that, let me do the cosine of theta f of g. This cosine of theta as the normal force that makes with the displacement, right? And then plus, the kinetic friction. So remember, I'm doing this part over here, right? Magnitude of the kinetic friction times displacement, then times cosine of theta that kinetic friction makes with the displacement. That's my net force. Well, one of the things you can see quickly is that normal force here is perpendicular to displacement. So this whole thing is 0. But you can see, right, gravity and friction no longer perpendicular, or the gravity is no longer perpendicular, so it's actually doing work. So that means if I'm writing this here is, then I have to find the work done by gravity, which is then mg times delta x, then times cosine of, so now I have the theta. You can say, right, what is this theta? Well, this theta, see, I have the alpha, so this is 90 degrees, And if I have alpha, the theta is nothing but 90 minus alpha. Okay, then plus the work done by kinetic friction. Well, what I'm going to do here is I'm going to use f of k equals, if you remember right, mu k times normal force. I'm going to use that for this. So f of k here is replaced with mu k times normal force. But here, see, the normal force is this guy over here. So technically it's mu k times mg cosine alpha. Okay, so that means I have mu k times normal force, then times delta x. And you can see, right, the theta for the friction, basically this guy over here, theta for the friction is displacement to the kinetic friction, from displacement to force, and that is 180 degrees. Okay, so this guy here is cosine of 180 degrees because of friction to be opposite of the displacement, right? So you get cosine of 180 degrees. And just that basically makes this cosine of 180, right? Remember, it's -1. So I end up with this. So mg delta x cosine of 90 minus alpha plus, then I have mu, so cosine of 180 technically gives me -1, so minus, then mu k for the normal force. So I'm going to basically say, okay, f of k is mu k times normal force. But then since normal force is mg cosine alpha, then I can rewrite it like that. So mu k times mg cosine of alpha, which is just a normal force, while cosine of 180 was the -1. So that's basically my equation. So, and what I can do here, I can already plug in values. So one thing you can see here is, I can factor out mg and delta x. So there's a delta x over there. So I can factor out mg and delta x. And what I end up is basically cosine of, well, it's 90 minus 24, right? So 90 minus 24 as an angle for that. So let me do this. 90 minus 24, I get 66. So cosine of 66 minus coefficient, which was 0.31, times cosine of 24. Kind of running out of room. All right, anyway, so the network is, and I can calculate, so mass was 5 kilograms times 9.8. Displacement was 2.8 meters. This is mg times delta x, and then factor out. So basically I have then cosine of 66, because this was cosine of 90 minus alpha, then minus 0.310, which is the coefficient, mu k, right? Then times cosine of alpha. Remember, this is, in terms of like from the normal force, and alpha was then 24 degrees. All right, so I can calculate this to get a total of 16.9 joules. So positive 16.9 joules. All right. That means the work done is a positive 16.9 joules. One thing you can see right in my lecture notes, I independently calculated the work done by the gravitational force, which was 55.8 joules, then independently calculated work done by the friction, which was negative 38.9 joules. You can see it in the slides, right? And then when you subtract them, you get 16.9 joules. Here I kind of did everything together, but that's kind of the idea. That means you can calculate the net work done by finding each individual work done and then add them together. Well, if one of them is negative, you basically subtract them. So then what we get from there is this. As the box, right, the package goes from point 1 to point 2, it gains energy. Well, if it gains energy, that means it's moving now faster. Remember, right, net work, or the total work done, is equals to change in kinetic energy. So K final which is 0.2, minus K initial, which is 0.1. Well, it had kinetic energy to start with because it was moving in the beginning. So one thing we can do here is then, that means there is a network, there is a kinetic energy. So I can calculate the kinetic energy at 0.2, which you can see, right, is equals to kinetic energy at 1 plus work done. Okay. So kinetic energy 1 was 1/2 times mass, which is 5 kilograms, times speed at 0.1, which is 2.2 meters per second squared, then plus 16.9 joules. And what we get here is we find the kinetic energy at 0.2, which is then 29 joules. All right. That means it's increased its kinetic energy. Okay. And then from here, we can go ahead and solve, because remember, kinetic energy 2 here is 1/2 mv2 squared equals 29 joules. And then rearrange and solve for the speed 2 from this equation, right? And what we'll get here is 3.41 meter per second, which means it's moving faster as it gets 2.2 because it was given energy, or there was an added energy to the system. Again, what we're doing here, we are looking at, not because it was speeding up or something like that, but we're looking at it moving faster because there was a transfer of energy into the system. All right, so let's continue. Now we are getting to that work done by a varying force. So one thing we have here is previous few examples that we considered, the force acting on the object was a constant force, okay? So that when friction acting, when the gravity acting, they are constant forces. And with a constant force, in a way, you can see, right, if you're doing the force as a function of position, well, force doesn't change as you go from 0.1, let's say, to 0.2. So under that, right, it doesn't change. The force is constant. But you can also have, when the force is acting, like you can see in this graph, right? You can see, right, when your initial position, there's a force acting on it. But then as you go from initial to final position, see, force increases. That means you have to push harder and harder and harder, right, to make the object move. So it's a varying force, a variable force. And the graph for that will look like something like this, right? So in a way, we're not necessarily equipped in this class to work with something like that mathematically, but there are several ways we can kind of go around to do that, all right? So because in higher level mathematics classes, like let's say in calculus, right, you learn, for example, one thing you can do here is if you have a graph like this, you can find the area under the graph, right? And area under the graph will allow you to find, in this case, for example, the work done, okay? And that's one of the things we can do. For example, we can take a graph, something like that, right? And we can calculate the area under the graph to find, the work done. Because remember, work done is equals to force times distance, and you are plotting force versus distance. So if you have a force versus distance graph, any graph you have, you can find the area under the graph and find then the work done. That means work done officially equals the area under the graph. Well, if you have something like this, obviously it's not easy to do that, but there are shapes that are relatively simpler for us to use. And we have an example that you guys can see that, you can also find the work done if you're given force versus position, right, as a graph. All right, so let's look at this. So a force acting on a particle varies with x. So calculate the work done by the force on a particle as it moves from x equals 0 to x equals 6 meters. That means we have a particle, for example, you can see right here's a particle at x equals 0. And this is our position A. So this is 0. So I have a particle, here's something over there. And then there's a force acting on it. Okay, here's a force acting on it. But this force is not constant because we can see from the graph, right? So it's 5 Newton, when you start pushing and it's moving, 1 meter, 2 meters, 3 meters, 4 meters. So technically it's constant 5 Newtons. But then, so as we go, so 1, 2, 3, 4, 5, you have the same force, same constant force of 5 newtons. But then this force decreases as you move from, you can see, right, point B, right, that, you get to point B, but as you go from point B to point C, so let's say this is XB and this is XC, the force decreases. And technically, when you get to point C, there is no more force. Doesn't mean you're not moving anymore. It just that means you're not pushing it. You just basically let go of the box. Okay, so you get here and you let go of the box. Okay, but you've been pushing the entire 6 meters. It just from 0 to 4 meters, it was a constant 5 Newton force. From 4 meters to 6 meters, you basically decreasing how much strength of the force you're applying on the object. Okay, now this is you can see, right, this part, at least it's a variable force, and that equation, work equals force times distance times cosine of theta, only can be used if force is a constant. That force can only be used if force is a constant. So technically, for the first 4 meters, I can use that. I can still apply that force. Or I can look at it from a different point of view. If I'm given a graph like this, what I can do here, I can find the work done by finding the area under the graph. Okay, so obviously I can't do the entire thing all together, but I can break it down into the 2 segments. Here's segment 1, and here's segment 2. All right, so you can see segment 1. So the work done, remember, it's area under the graph, is simple because area under the graph, right? I look at, the y, the changing vertical times changing horizontal. Well, changing vertical is basically my, the force, right? This is 5 newtons. And then here, this is just the distance. So base times height. So this will be 5 newtons times 4 meters. So I get 20 joules. All right, so then this is segment 1. Then work done for the segment 2. Again, it's base times height, but from the shape of, you can see, right? Hopefully you remember your, algebra classes, right? So to find the area for that is you do 1/2 base times height. So 1/2 base times height. Well, which will be 1/2 times 5 newtons times 2 meters, right? Distance of 2 meters. And then from that, what I can do here is I get then 5 joules. So the net will be adding those 2 together. So then I'm going to get net of, 20 plus 5. So 25 joules. All right. So that's the total work done by this particle. And then at the end, if I, let's say, want to know what is the particle speed when it gets to this point C, remember, then I can say that, this is equal to change in kinetic energy and use that and so on and so forth. Let's say if I'm given the speed at point A, I can then use that to find the speed at point C. All right. So that's, another way of doing that. All right. So the reason we do that, because when I'm looking at spring force or elastic forces, they're generally not constant. Remember this equation, right? Spring force equals K times X, or at least in terms of its magnitude, which means that spring force increases with distance. Remember, so here's, for example, the spring in its equilibrium position, right? And remember, we always take equilibrium to be X equals 0. So that's why you can see, right? If I look at what is the spring force when the object is in equilibrium? Well, it's 0 because K times 0 is 0. But as soon as then you change the position X, right? You move the spring from equilibrium, either compressing or stretching, then there's a spring force. And more you stretch or more you compress, stronger the force. Okay. Then one thing we can see is that if I take this force and I plot that, see, force versus position, because force is directly proportional to X, I'm going to get a straight line like that. Right? And you can see, right, this line represents, the force versus, displacement for the spring, elastic object. And one of the things we can see here is that if I find the slope of this line, I'm going to get, the constant K. But also what we can see is that I'm still plotting force versus position. And if I find the area under this graph, I'm getting the work done. Well, we can see, right, since this is 1/2 base times height, then work done by a spring is always equals to 1/2 k times x squared, since technically if I take this initial x and initial x being, object in equilibrium, where x is 0, I can find that spring force or work done by the spring force is 1/2 times k times x, which is how much it's being stretched or compressed, squared. All right, so that's kind of like, what I will get with this equation. Okay, so here's one example, which I kind of explained this in the previous chapter, because whenever you have a force or the spring, right? Remember, one of the things we can do here is we can always find the spring constant by hanging spring vertically, attaching a mass, waiting until it's in equilibrium, then measure the distance, which is how much it's moved from, equilibrium position. And because at that position, the spring force acting on it will be equal to the weight of the block attached or the weight of the object attached. So we can use that to find the spring constant. But anyway, so let's look at this example. A spring is hanged vertically and an object of mass m is attached to its lower end. Under the action of the load, mg, the spring stretches a distance d from its equilibrium position. Now, if the spring is stretched 2 centimeters by a suspended object having a mass of 0.55 kilogram, what is the force constant of the spring? And how much work is done by the spring on the object is stretches through this distance. All right. So then one of the things I can do here is, remember, so basically if this is the spring, then if I attach the mass, remember, eventually this mass is gonna come to rest because the gravitational force will be balanced by the spring force. So then what I do here is I measure this distance d, which is the stretch distance. Remember then k times this d, which is the magnitude of the spring force, is equals to magnitude of the gravitational force, which is mg. Then k here is then mg over this d will allow me to find the spring constant. Well, that was a 0.55 kilogram object. So we can use this to find its weight. Then divided by the distance, and remember it was stretched by 2 centimeters, so 0.02 meters. We have to convert it to meters. And if I calculate this, I'm gonna get 270 Newton per meters. So that's, right, so it's 270 Newton per meter. That's the spring constant K. That was part A. And part B, then I can say, all right, so how much work was done as it moves this displacement of 2 centimeters? Well, then work done, let's say by the spring, is then just 1/2 kx squared or kd squared, let me put it like that. So it's 1/2, 270 Newton per meters. And then d was 0.02 meters squared. So then technically we can calculate this as, 5.4 times 10 to the negative 2 joules, right? So then the amount of work done was this, okay? So now, one thing we can see here is this. So let's say when we start from this position, this is being position 1, so we move to this position 2, you can see, right, then displacement is down. So this is my displacement as a vector, it's down. And then you can see, right, the spring force, technically, remember, this is for the spring force, right? Spring force the whole time was acting in the opposite direction of that displacement. So then in a way, this spring force does negative 5.4 times 10 to the negative 2 joules because the entire time it's acting in the opposite direction of displacement. That's why the work done by the spring force here is negative. All right. Then here we already talked about gravitational potential energy, but we're going to look at gravitational potential energy in a little bit more in greater detail here in this few sections. But remember one thing, right, is the gravitational potential energy is due to the change in height of the object, right? So whenever the object changes vertical position, gravity is acting on it, right? So, I mean, the gravity acting on it every time, but, let's say if you move the object above the table and you let go, you can see, right, the object is basically dropped. And when it's going down, the gravity is pretty much acting on it. So that's kind of what we have. That means this gravitational potential energy is kind of stored potential energy. So for example, here you always get a reference position. So let's say, let me do it over here, right? So let's say here's a reference position, y equals 0. And then every time you take the block, this block, so, and you move it some, you can see, right, some height above the, reference position, then you store energy. So then how do you store energy? Well, remember, so the block is not gonna on its own go to that height h, right? Somebody has to take the, the box, right, and just move it up. Well, if I take it from the ground and start moving it up, I'm basically doing work and I'm transferring energy into the system, right? So let's say things like this. Here's the block, and if this is my reference position, it has no gravitational potential energy, because here's the equation for gravitational potential energy, mg times y. Well, y is 0 here, this position, so it has no gravitational potential energy. But let's say here's a person, takes the box and moves it from here to there, right? So move it from here to there. All right, so when I move it from here to there, remember, what the person does, it applies force upward. So this is applied force from the person, and it moves it to this distance d above that, right? Well, you can see where the force of the person is in the same direction as displacement. That means work done by this person is positive, because it's doing positive work, pushing in the direction of the displacement. At the same time, the gravity is doing work done while the box is moving up. So technically the work done by the gravity when the box is moving up is then negative, right? Because gravity is acting in the opposite direction of displacement. I'm talking about this is during the time when the box is moving up, okay? But in any case, so if the person doing work, which is take the box moving upward, that process transfers energy into the system. That means when we come back here and we look at the box right here, right? A box has some height above the ground and it has this stored energy. So we can say that, see, this is position y, which is not 0 anymore because this is my 0 position. So then this position y allows me to calculate gravitational potential energy. So let's call this position 1, okay? So this is position 1. I have then mgy1. That's my gravitational potential energy, okay? So for example, let's say this y1 is 1 meter above the ground. So then if I calculate, and let's say this is a 1 kilogram object, then I can put, 1 kilogram times 9.8, then times 1 meter height, I'm gonna get then 98 joules. That means if I move 1 kilogram object 1 meter above the ground, I store 98 joules of potential energy. And that potential energy is a stored energy, okay? So then after that, what I can do here is I can start with that energy, okay? So that means I can say that at that instant when the box is at 1 meter above the ground, and let's say I'm holding, it has stored energy. 1 meter above the ground, 1 kilogram object, I stored 98 joules of energy, okay? So now what happens when I let go of that energy? I let go of that box. Well, if I let go of that box, what happens is, we know, right, it's gonna fall down. Well, when it starts falling down, you can see, right, closer it goes to the ground, smaller its height. Well, smaller its height, smaller its potential energy. So for example, if I wait until the box is somewhere over there and calculate potential energy at that point, I'm gonna get something less than 98 joules. Why? Because the height is less. That means I decrease my potential energy. Well, when the potential energy is decreased, that means you lost potential energy. But technically what we have here is that, remember this conservation of energy. So there's this conservation of energy that tells you that energy cannot be created or destroyed. That means if you lose energy, that's only because it has been converted to something else, some different type of energy. Well, the type of energy it has been converted to is kinetic energy, because you can see, right, if you drop something, as it's falling, it's going to be moving faster and faster. How is it moving faster? Well, it's converting some of the potential energy that we stored into the kinetic energy. So that's why as as that box is falling closer and closer to the ground, right, getting closer and closer, it's moving faster and faster because the potential energy decreases as the object going down, but then kinetic energy will increase because the energy is converted from potential to kinetic. All right. So that's kind of one of the things we can have, because you can see what happens here is that, see, here's 98 joules of potential energy at point 1. And let's consider point 2 here is the ground. What is the potential energy at the ground? Well, if the ground is my reference point, remember, if I put mg y over there, because y is 0 at that point 2, well, I'm going to get 0. That means my potential energy at point 2 here is 0. So that's why you can see, right, when I go from point 1 to point 2, I'm decreasing my potential energy. It goes from 98 joules to 0. That means what I have here is that if I'm looking, changing my potential energy, which is y2 minus y1, potential energy at point 2 minus potential energy at point 1, I'm going to get negative 98 joules. Okay, I'm going to get negative 98 joules. And what I have here is then my potential energy will decrease as the box going from point 1 to point 2. Okay, that's one thing you can think of always, as if you increase the height of the object, potential energy increases. If you decrease the height of the object, potential energy then decreases. That means further you go from equilibrium, if you increasing, right, you are increasing kinetic and potential energy. But if you go toward the this reference point, not equilibrium, so reference point, right, you are then decreasing the potential energy, because potential energy at the reference point, which is position 2 over here, right, in this example, it has no potential energy. All right, so here's then what we have. So if you come, if you consider then again same thing, right? So let's say if this was the block or the box. So let me just represent as a particle. So here's the particle, right? And let's say this is my ground. Remember, I'm saying that this is point 1 and this is point 2, and position of point 2 here is 0. Okay, position point 2 here is 0, and position of point 1, let's say 1 meters. And then, as we said, potential energy at point 1 here is 98 joules. Potential energy of point 2 here is 0. Hopefully at this point you know why that's the case. If not, just maybe go back and watch it again. Now, what happens here is this, thing like this. If you at position 1, so let's say if you're at position 1 and holding this particle, this object, think like this. After I let go of this particle, what happens here is the only force acting on it is gravity, right, F of G. And then the gravity is going to pull it down from point 1 to point 2. Well, when the gravity acting on it, so you can see, right, it goes from this point 1 to point 2. See, this is the displacement, right? This is my displacement. Let's say this is delta y as a displacement, force as a vector, right, acting down. You can see, right, I can calculate the work done by this force, which is its magnitude, mg, then times delta y. So mg times delta y, which is the displacement, then times cosine of theta. Theta is between force of gravity and displacement delta y. And you can see both of them in the same direction. So that means theta is 0. So it's basically mg delta y. But hopefully at this point, you can see that work done by gravity, in this case, technically is positive, right? So you can see, right, work done by gravity is positive because when the object is going down, force is in the same direction, down. So work done is negative. Work done by gravity in this case is positive. Well, when work done by gravity is positive, that means, when you go from point 1 to point 2, which is falling down, one thing we just talked about is that your gravitational potential energy decreases, right? Because you go closer to your reference point in this case. Well, which means that there's an important relationship there. And what we have here is this, the slide kind of talks about that. You can see, right? The change in the potential energy due to the conservative forces is related to the work done by the net force. Let's talk about what do you mean by conservative force? Well, conservative force is a type of force that conserves energy. Is gravity a conservative force? Yes. Gravity is one of the 2 conservative forces that we have. So here's the gravitational force as a conservative force. Second is the spring force. So those are the two conservative forces that we're going to consider in this chapter. Okay. That means every time you have just gravity doing work, it does not change the system energy. It only changes energy from one type to another. Same thing with the spring force. When the spring force is acting on the system and only spring force, it does not change the energy of the system, but it converts energy from one type to another. But anything else, like let's say when you're pushing something, when you're pulling something, right? Tension, friction, they change energy of the system. So they are called non-conservative forces. Other forces conserve energy, we call them conservative forces. And two examples of those conservative forces in this chapter is the gravitational force and then the spring force. Because think like this. So this is 0.1 and this is 0.2. See, let's say if the total energy of the system is 98 joules at 0.1, that means total energy of the system is also 98 joules at 0.2. It's also 98 joules at some 0.3 or at some 0.4, anywhere, right, during that motion. If I stop, freeze, and measure total energy, I'm going to get same total energy in the system. So that's why we call that conservative force, because they conserve total energy of the system. They don't change it, all right? Now, one of the things we have here is then there's this relationship then. That means when the gravitational force doing positive work, it changes potential energy, but changes potential energy such that, you know, when gravity doing positive work, then potential energy decreases. Again, you can see from this diagram, right? See when the object going from 0.1 to 0.2, remember it has a higher energy at 0.1 and going to the lower potential energy at 0.2, right? So basically potential energy decreases as it's going down. But if I'm looking at the work that gravity doing as it's going down, well, the gravity doing positive work because it's acting in the direction of the displacement. So, but if I'm then considering another thing, so let's say here's the particle at 0.1, which is now the ground, let's say, and then going to this 0.2, which is some height above the ground. Well, here's the thing. This is, let's say, the displacement vector, right? That means this is where the displacement of the particle is, right? Upward. But remember that as the object is going from 0.1 to 0.2, gravity in this case is going to be acting down, because it's always down, right, toward Earth. That means in this case, as the particle going up from 0.1 to 0.2, well, work done by gravity is negative because it's doing negative work, because you can see, right? So if I measure this data, it's now 180 degrees. So that means it's gravity doing negative work. But while gravity doing negative work, in this case, you can see, right? If I look at energy at 0.1 and compare it to energy at 0.2, for this particular case, I'm going to get 0.2 have a greater potential energy because it's higher, right? So that's why you can see that what you have here is that if the gravity doing negative work here, potential energy increases. But in the first example, which is this one over there, when the gravity doing positive work, that means you are moving in the direction of gravity, your potential energy decreases, okay? So that's why this equation then gives you that. Work done by the gravitational force, or technically, here's the thing. This is true for any conservative forces. When a conservative force doing positive work, your potential energy then will always decrease. So that's why we present that relationship. Work done by a conservative force equals negative delta U, okay? So that's kind of what we have. Here's then what we get. Let's say, let me, for example, do this. So I'm gonna stop this. All right, so I'm gonna use this right now to kind of explain that. All right, so think like this. So here's our particle. Let's say this is 0.1. So it's gonna go from 0.1 to 0.2. Okay. Now, one thing we have here is this. So as it's going down, let's say this is the displacement vector, right? Here's the displacement vector. And then as it's going down, this is the gravity acting on it. Well, then I know one thing, is that work done by then the gravitational force is equals to changing gravitational potential energy, right? So this is, this is true for any conservative forces. In a way, you can think of like contribution to the conservative forces is that they change the potential energy of the system. But we also learned another equation a little while ago that work done is also equals changing kinetic energy of the system. And this is work energy theorem. This is any type of work done. Any type of work done equals delta K, but only conservative forces, when they do work, is equals to negative delta U. So right now we are working with a conservative force. That means if the work done by conservative force equals negative delta U. But again, exactly same time, this is also equals to then delta K, because work done by any type of force generally will go also then equals delta K. Well, what I have is then this, then delta U, remember, this is negative. So U final, or, let me do it like, or U final, let's say minus U initial. This is, remember, delta U is equal to that. So negative delta U means negative U final minus U initial. So then technically what I have here is this, if I use this then negative and distribute, so it becomes negative U final plus U initial. All right. That means this negative delta U is equal to this. That means here I can write this left side as U initial minus U final, right? Because negative delta U just ends up being U initial minus U final. And then this is equal to delta K, which means K final minus K initial. All right, so I end up with that. Now here's what I have. If I then rearrange, move the initials on one side, finals on another side, I end up with this. U initial plus then K initial equals then U final plus K final. And this equation is the conservation of mechanical energy. Conservation of mechanical energy. Because gravitational force is a mechanical force, and we can say then it's a conservation of mechanical energy. All right, so it means that this is initial, this is final. So technically, again, one thing we can say here is it just means 2 points. So let's say I can also write this as U1 plus K1. That means sum of kinetic and potential energies for point 1 is equals to U2 plus K2, sum of the potential and kinetic energy for point 2. All right. So this U represents potential energy. And in a way, because I have 2 types of potential energies, I can say this is UG1 plus U, elastic 1. Remember, we talked about that. Then plus kinetic energy 1 equals then UG2 plus U elastic 2 plus K2. And I can use this to basically represent 2 points during this motion of the object. So this is true if only conservative forces acting on it. And let's say as the object is falling down, right? Well, I have work done only by gravity. That means gravity is a conservative force. That means it's going to conserve energy. That means what I have here is this. For example, if I drop the ball, some kind of, let's say, drop the object or a ball at point 1, dropping means, remember, speed at point 1 equals 0. What I have here is if I drop it, and I want to know how fast it's moving at point 2. So technically, I can use dynamics and kinematics to find the speed at point 2. But I can also use kinetic, energy approach. Because what I have here is that when I drop it, it's under this gravitational force. The motion is under gravitational force. In a way, then I can look at the whole thing from the point of view of energy. You can say, okay, since it's a conservative force, then energy at point 1 is the same as energy at point 2. So I can say this, energy at point 1 equals energy at point 2 because, work done is by the conservative force. Okay, and you can see, right, What is energy at point one? Is the sum of the energy types at point one, which is, let's say, gravitational at point one, plus elastic at point one, plus kinetic at point one. And then this is, let's say point two is the ground, right? And then this is going to be equals to the gravitational at point two, plus elastic at point two, plus then kinetic at point two. Now here's what I have. I'm going to take point two to be my reference point, 0. And gravitate, and then what I have here is, then let's say I want to find this V2. Think like this. So if I come back here, I can rewrite this as gravitational potential energy at point one is mgy1. All right, so I'm kind of like mgy1. Elastic potential energy, well, here's the thing, there's no change in shape. So technically, and this is 0, and this is 0. So I can ignore that. So then plus 1/2 mv1 square. And then gravitational potential energy at point two becomes mgy2 plus then 1/2 mv2 squared. But this particular example tells me that I start with rest. I start from rest, and then position 2 is my reference point, so it has position vertical as 0. That means I can come back and I can say this is 0. Well, and this is 0. Then what I end up with this, mgy1 equals 1/2 mv2 squared. That means at point one, my energy is purely potential. That means, remember, I'm holding a block, or I'm holding an object at some height h, right? So this at this position 1, and it's at rest. But because it has a height difference with respect to the reference point, which is the ground, there is a potential energy. But as I let go, it's going toward the ground, so it's decreasing its potential energy. But that energy cannot just disappear. What happens that energy then is converted to kinetic energy. And by the time it gets to the ground, all that energy now is purely kinetic energy. That's why energy at point one is all potential. Energy at point two is all kinetic. And one thing I can do from here, you can see that I can cancel the mass from both sides and then solve for the V2. And it's going to be then 2 times g times y1, 10 the square root. And I can use this equation to find the speed at point two. And you can see it's very easy. I need to know, let's say, any forces between them, any acceleration, and so on and so forth. Just energy at point one compared to energy at point two. And I'm able to calculate how fast it's moving when it hits the ground. All right. So those are the things, let's say, we can do when we're considering, let's say, this energy approach. All right, so then let's do this. All right, so let's go back to the slides then. So here's one example there. Okay, a trophy being shown off by a careless athlete slips from the athlete's hand and drops on his toe. So choosing floor level as the y=0 point of your coordinate system, estimate changing gravitational potential energy of the trophy Earth system as the trophy falls. Repeat the calculation using the top of the athlete's head as the origin of the coordinate. All right, so imagine that, let's say, the athlete is holding the, let's say, the trophy close to his head, right? So let's say at the head level, and then let's say it drops, okay? So one of the things we can do here is, let's say you can see that, let's say here's the ground. Okay, let's say here's the athlete. Okay. And let me see. So taking then, for example, actually, let's say here's the trophy. I don't know, some kind of trophy like this. I don't know how the trophy looks like, but I don't know, something like that, like Stanley Cup or something. So let's say it's holding the trophy, and let's say the trophy here is, I don't know, 0.5 meter above the ground. Okay. So let's say 0.5 meters above the ground. All right. So then one of the things we can do here is taking the, let's say, the mass of the trophy, which not given in this example, let's say, but let's say it's a 2 kilograms. So let's say that's the mass of the trophy. So it's 2 kilograms. So I'm going to say that, okay, so we're going to start with this position 1, and I'm going to go hit the ground at position 2. That means I can calculate the potential energy at point 1, which is mgy1. And then you can see that if I do this calculation, so it's going to be 2 kilograms times 9.8 meter per second square, and then times the, the position 1, which is 0.5 meters. So we're going to get 9.8 joules. All right. So I get 9.8 joules. Okay. So here's then one thing we can do. So let's say, actually, let me do this. Point 2 here is because the problem tells you that, reaching a toe. So let's say toe is somewhere over here. And let's say point 2 here has a position of 0.03 meters. Okay, in my problem, I have that. That means, I can calculate the potential energy at point 2 as mgy2. So 2 kilograms times 9.8 times 0.03 meters. So 3 centimeters basically above the ground. That's where the toe is. All right, so if you calculate, I'm going to get 0.588 joules. All right, and then what I have here is here's a change in gravitational potential energy, which is U2 minus U1. And if I do the difference between them, I'm going to get negative 9.1 joules. All right, so I'm going to get negative 9.1 joules. Okay, so now, for example, that's my change in potential energy, which is negative 9.1 joules. Because as it's going down, the potential energy decreases. I'm going to do this then. Like, for example, the athlete's head here, let's say it's 1.5 meters. Okay. So let's say in this case, I have that, which is 1.5 meter above the ground. One thing I'm going to ask you then to do, you can do this at home on your own. So instead of using this coordinate system, use this. So then here's the athlete. So let's say it's holding the trophy like this, right? But take the position of the trophy, so let's say y1, to be relative to the, the head, which is, take this position to be y equals 0. Then y1 will be relative to that. And then y2, again, will be relative to that. Then calculate your potential energy U1, potential energy U2, and then find the difference between them. But this time instead of referencing the ground, or let's say the ground being 0, right? Let's say you use the head to be 0, and then try to do this. And one thing you will see here is you're going to get exactly that number, right? So go ahead and do that calculation, and if you have any questions, let me know. But you should be able to get exactly the same thing. All right. So to continue with this, so let's see in terms of energy stored in the spring displacement. So this was, remember, this was a elastic or spring potential energy, and I gave you this already. But one of the things, is kind of like new that we can talk about is that any elastic force, spring force, for example, is a conservative force. That means if the system is under the spring force, well, conservation of energy will occur. And then as long as the only force in the system is the spring force, then you can assume that energy at any 2 points, right, again, will be the same. So, but one of the things you can see here is that, for example, right here, the spring system is in equilibrium. You can see, right, you have the spring and you just attach the mass, but the spring is neither stretched or compressed. So we take that equilibrium position to be x equals 0, and then elastic potential energy is 0 when the spring is in equilibrium. Just like the gravitational potential energy is 0 when the system is at the reference point. And every time you change the, position of the block relative to the equilibrium, then there's an elastic potential energy, because let's say it's equals to 1/2 k times x squared. So how much you stretch or compress, then you basically can calculate the amount of stored potential energy. Because imagine you take this block and you move, let's say you stretch it to this distance, you can see this force magnitude. Well, you stretch it more, you can see again magnitude of the force increases, because it depends on the displacement. But one of the things we can do here, looking at this equation for the elastic potential energy, we can see that more you stretch or more you compress, more energy you store. More energy you store, then faster the spring can move when you let go of the spring, which you can kind of visualize that as well, right? So again, here's the one example that we can always use for the conservation of energy, or conservation of, like, let's say, mechanical energy. So we start with this, let's look at the picture A. You have a spring in equilibrium at x equals 0. Then look at the energy bar over here. Well, there's no energy in the system because not in the spring, or the spring block system is not moving, everything is in equilibrium, right? And so on and so forth. And then let's bring a block and not attach to the spring, but at this point I'm going to use the block to compress the spring. So let's say when we have this compression x, so basically we start pushing, right, the block, which compresses the spring. Well, as the spring moves from equilibrium, there's a potential energy in the system because you are storing energy. Well, then total energy then will be in terms of the potential energy now. But then what I can do here, I can, compress it more. Let's say this is X max. Then let's say you compress and you stop. Well, when you compress and you stop, then all the energy you can see, right? So like this is total energy, which is in terms of kinetic and potential. All right, so let's call this, I don't know, 0.1. So you can see, right? So you can say total energy, this is 0.1. So it becomes K1 plus U1. But because we're holding this guy, the all energy is just purely potential, right? But what happens if you let go of the block? Or as soon as you let go, then it is being pushed toward equilibrium. That means the spring force gonna do work. As the spring force doing work, it pushes the block toward equilibrium. As it pushes the block toward equilibrium, it decreases potential energy. You can see, right? As you get to this position 2, which is not quite the equilibrium position, right? But you're getting closer to equilibrium position, means as you move toward equilibrium, your potential energy decreases. Look at how much it decreased. But potential energy decrease means that kinetic energy would increase, because you cannot destroy energy. If you're decreasing energy as one type, you're increasing energy as another type, because E1 is E2 equals to E2 at any time. And this is then K1 plus U1. So for example, right, if here I have 100 joules of total energy, well, when I started at 0.1, my 100 joules was all potential energy. But now my 100 joules total energy is maybe, let's say, 20 joules potential, but then 80 joules kinetic, because as I lost 80 joules of potential, I gained 80 joules of kinetic. And the total is still 100 joules. But then what happens here is that here's then, let's say, some 0.3, right? That means 0.3 is when the spring comes to equilibrium. When it comes to equilibrium, let's say that instant, right? We're considering that because the block is not attached to the spring, it's going to continue moving. But if you're looking at energy at 3, well, because there is no, the potential energy, because let's say you're in equilibrium, that means all energy is now kinetic. You can see, right, all energy is kinetic. And, that means it has to be then 100 joules, because that total energy in my system was always 100 joules, right? That means elastic potential energy was converted to kinetic energy as we moved from 0.1 to 0.3, right? So the entire time, as the spring force was doing positive work, the kinetic energy was increasing, but the potential energy was decreasing. All right, so here's another example that you might see. You might actually have an example where all 3 of those and the type of energies we can, come into play. So here's an example where you have an elevator, right? So let's say elevator generally have a safety, springs at the bottom, where when the elevator is, let's say the cable breaks and it's falling, right? It doesn't fall and hit the ground. It goes and hits some kind of spring, which then compresses, and it allows then, to that kinetic energy of the elevator be converted to the potential energy, or gravitational, spring potential energy of the system, and eventually comes, and slows down and stops the elevator. Okay, so let's say then we have 2 points of interest, right? So here's the initial position, or the initial position where the elevator hits the spring, the spring that was not compressed initially. That means it hits the spring with the speed of 8 meters per second. You can see, right? And what it does is then it compresses the spring, right? Compresses the spring by 3 meters. And by the time it compresses the spring by 3 meters, right? And then it converts all of its kinetic energy to the gravitational, or let's say the spring, potential energies. All right. So this is going to be my initial position. What I'm going to say then, I'm going to say my initial position equals 0. All right. So then what will be my final position, which is this guy over here? Well, it's 3 meters below that. So I'm going to say it's 3 meters. Okay. And the end result is that final velocity of the elevator is 0. Now, here's what I have. I can say that the entire time, the only thing acting on the elevator is the, gravity and the spring force, right? Because the gravity, pulls down the elevator, but then the spring force acting in such a way that it slows it down, right, and stops. But the idea here is that the entire time you have gravity and spring force. And remember the important thing about gravity and spring forces, they're conservative forces. That means I can easily say that energy at initial position is the same as energy at the final position, because energy is conserved. What is energy at initial position? Well, it's in terms of kinetic energy, and then gravitational energy, and elastic energy. What is energy final? Well, it's in terms of kinetic energy, gravitational potential energy, and then elastic potential energy. Okay, so this is my equation for the energy. This is total energy before equals total energy after. Again, doesn't mean that every single type of energy are the same. The sum is the same. Now, what I have here is this. If I'm looking at my system, initially I had a kinetic energy. So this kinetic energy is not 0. So this is non-zero. But at the initial position, right, that's my reference position, y equals 0. Well, means, think like this. If I write it down, right, 1/2 mv initial square plus mgy initial, then plus 1/2 ky squared. That's my initial before, the energy before. And this is equals to, so basically 1/2 mv final square plus mgy final plus 1/2 ky final square. That's my then energy after. Then from here I can simplify. I can say that my initial position is 0, which means this is 0. And since that's also my, the unstretched spring, that means that's also my equilibrium, so this is 0. And then when I get to my final position, there is no speed, so that guy here is 0. That means what we have here is this, 1/2 mv initial square equals mgy final plus 1/2 ky final square, which means my energy before was all just kinetic, but then my energy final is gravitational and spring or elastic potential energies, and there is no speed, which means effectively we were able to stop the elevator and by just absorbing the energy, kinetic energy, right, and converting into gravitational and potential. So one of the things you can see here is that in a way, the only thing we can probably calculate in this case, since we're given the mass and we're given the initial speed and we're given the displacement, right, this y, So maybe you can calculate the spring constant K over here, because that's the only thing we're not given. Maybe you can use this to calculate spring constant K. All right, so do it yourself and see what you get. All right, so then here's what we have. That means this is the using a law of conservation of energy. The idea is this: energy before and after, so in energy before and after, exactly the same, only if work done is by conservative force, okay? That means when the conservative force doing work, your energy is the same before and after. But what happens, if the energy is not conserved? What are the conditions for energy not to be conserved? Well, that means every time your forces include like friction, tension, push, pull, apply force, something like that, well, that means there's, the energy is no longer is conserved, okay? And one of the things we can do here is we can understand that energy is not conserved due to some kind of work done by non-conservative force. So then technically what we have here is we have two equations. Equation 1 represents this. So think like this: you have delta E, right? Change in energy, which is basically E final minus E initial. Okay, E final minus E initial. Remember, if E final and E initials are the same, then you basically get 0, right? That means delta E equals 0. Well, delta E equals 0 means that energy is conserved. Or condition 2, where delta E, which is E final minus E initial, is not equals to 0, which means that energy before and after not the same. Well, if they're not the same, that means something changed the energy before compared to before and after. And remember, one thing we learned here in the first few examples is that, well, if you're doing work, positive work, net positive work, right, you can change the energy of the system, right? So, but if you remove energy of the system, then you can again change it, but in a way that you can decrease the kinetic energy or things like that. The idea here is this: these two conditions apply to, in terms of condition 1, will be always only true if the gravity on spring force acting in the system alone. But if there are other forces, or like friction, pull, apply, things like that, right, then you are working with condition 2, right? So that's kind of what let's say we can think of. And the idea here is that this delta E, which is change in energy, and remember, energy itself was kinetic potential, right? So you can think like this is nothing but changing kinetic energy plus changing gravitational potential energy plus changing elastic potential energy, right? So that's kind of what we have. But we can also include this change in thermal energy. So what is change in thermal energy? Well, that's a contribution from friction, okay? Contribution from friction, because friction then can technically remove energy from the system. But remember, my system can technically include the surface, so I can also use that as well, right? So the idea is that this change in thermal energy, technically the equation of that is kinetic energy times my displacement, right? So that's a equation for change in thermal energy. That means amount of energy that is removed by friction, which goes always into heat, right? That's why it's thermal energy. But if I take the surface as part of my system, then I can say that it's just nothing but some of the energy now converted to the friction. That's about it. It's not lost, it's just converted to, let's say thermal energy, right? I can also look at it in terms of that. That means this is no longer mechanical energy because I'm including that. So this is just mechanical energy. But if I include friction as well, right, or the heat energy or internal energy, thermal energy, right, I'm talking about the total energy of the system, okay? That means this is my total energy of the system. It's always going to be then equal to the work done, okay? That means I have to do some kind of work in order to change any of those things. And, in terms of the work done here, it has to be by non-conservative, NC, non-conservative. Because if the work done by conservative force, like force of gravity or force of friction, then energy of the system will not change. It will be the same before and after. That's what you can see, right? Then technically what I can see here is this. I can isolate my system such that work done by non-conservative forces is 0. That means, I'm only including things like gravitational force or spring force. And then also if I can include the thermal energy, okay? So if there's a friction, I can also include that as part of my isolated system, okay? That means I'm not considering any type of push, pull, tension, and thing like that. I'm only considering an isolated system. So that's kind of like in terms of what we have for the isolated system. That means isolated system assumes that work done by non-conservative forces equals 0. That means gravity, spring force, or the friction, which basically contributes to the thermal energy, right? Those are the things that can be part of my system, okay? So that's why we get then this grand, sort of like grand equation for the conservation of energy. And this is again for just 2 points, right? Initial point and final point. I'm looking at kinetic initial, gravitational initial, and elastic initial. That's basically my total energy at initial point. And I'm saying that it's going to be the same as the total energy at some later position, for example, right? So where if I add kinetic, gravitational, elastic, and then contribution from the friction, if I add them all together at that final point, I'm going to get exactly the same thing as at the initial point, right? So that's kind of like the idea of that. So in a way, you can figure out, do I have that or not? Do I have somebody's pushing or pulling, right? Remember, I'm talking about just during the motion. You might be pushing the block and compressing the spring, but then when you let go, the object is moving without that push, right? It's basically being pushed by the spring itself. So, and let's say we're only considering when object is moving after you let's say, let go. Okay. So let's then look at in terms of what we can see, right? So it says, all right, so choosing an isolated system. Okay. So here's an example, an object in free fall. We choose the ball and the earth as the system so that the forces between them are internal forces. Remember, then I can choose that gravity to be in a way, like let's say, here's my object and I want to see what the object is, how object is changes its motion due to gravitational force, and I can then ignore everything else, right? And an object sliding down a frictionless ramp. Well, if it's frictionless, right? So that means, I can look at, right? External force and ramp exerts on the object is perpendicular to motion, so it does not work. An object and earth together form an isolated system, okay? That means, again, the only thing making it move is the gravitational force, okay? And it basically allows the object to go from top of the incline to the bottom of the incline. An object compressed by a spring, or an object compressing a spring. We choose the object and the spring to be system. The force between them are internal forces, so no work is done. And in a way, one of the things we can do here is that the spring then goes into just, conserving the energy, right? All right, so then object sliding along a surface with the friction. Well, here's one thing I can have here is that if I'm taking then, you can say, right, the block and the surface together as my system, then whatever energy the block is losing because of the friction is just gained as a thermal energy by the surface, right? So you can see, right, in terms of then, because it's isolated and I'm including the surface, then the kinetic energy is lost by the block, but it's gained, surface then gains thermal energy, so then I can have them together. Okay. All right, so okay, so let's look at then this example over here. Okay, so while at the country fair, Katie tries the water slide, whose shape is shown in the figure. So you can see, right, it's unusual. It's not like incline. So if I try to solve this problem using the, let's say, Newton's laws, I can't because of the shape of the, incline. But if I try to use the same thing, using energy approach, I have no problem with that because all I need to know here is this is 0.1, and let's say this is 0.2. the top of the incline, the bottom of the incline. And one of the things I have here for the conservative forces, right? The way the object moves from point 1 to point 2, it's independent of the, the path. So the incline could be the way it's shaped like this, or it could be like this, or it could be like that, or it could be like this, or it could be like that. It doesn't matter. All I need is point 1, point 2. And what I can say here is that, because you can see, right, the starting point is 9 meters above the ground. She pushes off with an initial speed of 2 meters per second. And it says, if the slide is frictionless, how fast will Katie be traveling at the bottom? That's the key, frictionless surface. So if it's a frictionless surface, that means independent of how the, let's say, the shape of the incline is, I can for sure say that energy at point 1 is same as energy at point 2. That's it. Same energy, because the only thing is the friction, only thing that acting on the object carry right here is gravity, because normal force always going to be perpendicular to the, let's say, the path, right? And gravity is a conservative force. It conserves energy. That means I can say then kinetic energy at point 1 plus then gravitational energy at point 1 is equal to then kinetic energy at point 2 plus gravitational potential and at point 2. And what I'm going to do here, I'm going to say then position of 2 is 0. And you can see, right, position of 1 is 9 meters. And then velocity of 1 is 2 meters per second. That means the only thing I can simplify here is since there is no position, or position is 0 at, or vertical position of 2 is 0, then I can cancel this because there is no gravitational potential energy, because that's my reference point. Well, K1 is 1/2 mv1 square plus mgy1 equals then 1/2 mv2 square. Again, final initial, remember you can write it as 1 and 2. One thing you can see here is I can cancel the mass from everywhere, okay? It's independent of the mass if there's no friction. Then what I get here is this, 1/2 v initial square plus gy1 equals 1/2 v2 square. So one thing I can do here is I can multiply both sides by 2 to get rid of that 2 over here, right? And switch the sides. So what I end up with here is this, v2 square equals v initial square plus 2gy initial. Right, so once I distribute this 2 inside, right, so I get that. And then take the square root of both sides to get v2 square. All right, so then v2 is equals to square root of v initial, which is 2 meters per second square, then 2 times 9.8 times 9 meter height. Well, we get 13 meters per second. All right, you can see how easily I was able to find the speed at the bottom of the incline, even if something as unusual shape as that for the incline. Because there is no friction, because there's only conservative force acting on it, I could, calculate the speed at the bottom by, using the conservation of mechanical energy. All right, so that's kind of one thing I could do with energy approach, and you can see how easy I was able to find that. All right. Here's one more example. Right, so the student places her 500-gram physics book on a frictionless table. She pushes the book against the spring, compresses the spring by 4 centimeters, then releases the book. What is the book's speed as it slides away? And the spring constant given as 1250 newtons per meters, 1,250 newtons per meters. Again, so as the student pushes the book, right, compresses the spring by 4 centimeters, that means after that, the only thing acting on the, on the book is going to be the, the spring force, because then you let go, the spring force is going to, push it to the left. But what we do here is the student's contribution is that by pushing and compressing the spring, we, transfer energy into the system as a potential energy, right? Basically, there's a potential energy, stored energy available then to start with. All right, so in any case, so one thing we can do here is we can call this position 1, and then as you let go, the spring is then pushes the book until you reach the equilibrium, right? This is position 2, so 1 and 2, and then at point 2, the book is moving with some velocity too, and that's what we want to find. Again, the spring force is the only conservative force, right, acting on it during this entire time. And technically there's gravity acting too, right? But remember, the gravity on the book acting such that here's the displacement, here's the force, it's perpendicular, so the gravity not doing any work in this particular case, all right? All right, so then I can say that energy at point 1 is equals to energy at point 2. Now I have kinetic energy at point 1 plus elastic potential energy at point 1 equals then kinetic energy at point 2 plus elastic potential energy at point 2. Well, I can simplify because you start with, you can see, right, releases the book. That means the book has no kinetic energy at point 1. And you can see, right, spring then reaches the equilibrium at point 2. So there is no elastic potential energy at point 2 because it reaches the equilibrium. Then what I get here is elastic potential at point 1. That means energy at point 1 is all purely elastic. And then it converts to kinetic energy at point 2. So then we have 1/2 kx squared equals 1/2 mv2 squared. Kinetic energy at point 2 is basically due to the fact that you had a potential energy at point 1, now you completely convert it to kinetic energy. All right, so I can easily cancel 1/2 and then solve for v squared. You can see, right, I can switch the sides. So v2, so v2 squared is equal to then kx1 squared over the mass. And then I take the square root of both sides to solve for v2, right? So equals to square root of, so 1250 newtons per meters times 0.04 meters squared divided by mass of 0.5 kilograms. All right. Well, if I do that, I'm going to get a speed of 2 meters per second. Okay, speed of 2 meters per second. All right. So again, another example of a conservation of, mechanical energy. Again, I'm calling this a conservation of mechanical energy because, there was no non-conservative forces. That means, mechanical energy is due to the kinetic and potential only. There are no thermal energy involved in this case because no friction. Okay, right? It's a frictionless table. All right, so then what we have here is, so let's talk about conservative and non-conservative. So basically, again, so summarize all of these things that I kind of mentioned this. So when only conservative forces acting, right, then we could use the conservation of total mechanical energy. You can see, right, so this kind of tells you that if spring or gravity as forces acting on the system, either only one out of those two or both of them together even, right, still energy is conserved, mechanical energy is conserved, because mechanical energy, if I'm writing like that, is kinetic plus potential. Let's say potential gravitational plus potential elastic. Okay, so this is mechanical energy. Then energy of the system is then mechanical energy plus, let's say, the thermal energy. You can kind of think of it like that, right? Thermal energy. So, and this is kind of like depends, right? So let's say if you want to include the surface as part of your system. But for example, if you're not including surface, okay, so let's say not including surface, that means surface is not part of your system. And if it's not part of your system, then the friction that it can, exert on your object can technically then dissipate the energy of the object, energy of your system. So let's say if you have just the block, your system, not the surface anymore, right? Then the friction can slow it down, right? Imagine if your block is moving on a surface, if it's frictionless, then the friction has no effect on its speed. Where there's a friction, it's going to slow it down. So then its speed will change, or kinetic energy will change because of that friction. All right, so then one thing we can do here is this. So I can say, all right, so change in then mechanical energy, that means energy, mechanical energy 2 minus mechanical energy 1, which is and mechanical energy between any 2 points, you know, will change if you have the work done by some non-conservative, right? NC. Remember, the friction itself also can be considered as a non-conservative force because friction is a dissipative force. So again, in a way you get like, this is for the mechanical energy, right? So you can kind of think of it like this. Under which condition is the mechanical energy is conserved or not? So here's equation 1. So mechanical energy conserved, that means delta EM equals 0, which means before and after is exactly the same. If the work done by non-conservative force equals 0, you can think like that. And this is condition 2, if the work done by non-conservative force is not equal to 0, right? If it's not, then your mechanical energy will change. So let's say in the previous example, if you're going down an incline, if you have 100 joules of total mechanical energy at the top, but only 60 joules of total mechanical energy at the bottom, well, that means your energy before and after is different, right? It's different by 40 joules. So what is that 40 joules? Well, 40 joules is the work done by a non-conservative force that removed it. Let's say in this case, if you calculate before and after, you're gonna get negative 40 joules. It's negative because it's being removed. So the object, right, has less energy at the end because of the, let's say, because of the friction. Okay. So those are the kind of things that we have. And one very important thing about conservative forces are that, as I mentioned, the conservative force is independent of the path. When you go from your initial position to your final position, if you're talking about conservative forces, it doesn't matter how you go there. So that means all you care about is energy before, energy after. That's it. And if you kind of calculate going one direction and then coming back in opposite direction, then for the round trip, if only for the conservative forces, you can say, right, when the starting and ending points are the same, to the total work done is 0. That means if you're considering only conservative forces for the round trip, right, if you calculate the work done in one direction plus work done in opposite direction, you should get 0. If this condition 1 and condition 2 are satisfied, then you know you're dealing with the conservative forces. Okay, so that's one of the things we can kind of consider that. All right, so the last concept we have here is concept of power, which basically considers the rate at which we transfer energy or the rate at which the energy is used. Because for example, you go from point A to point B and transfer 100 joules. Well, how long did it take? Did it take like 1 minute, 5 seconds, 10 seconds? So what we do here is we calculate the rate. So let's say some number of joules was transferred this unit of time. And then what we can do here is take the work done, and so let's say here's the work done divided by time to technically that, right? So, and we define this to be average power, okay? Average power. And power is joules per second, but we define the units to be just watt, okay? So that's why if you probably have seen, right, a light bulb or something like that, let's say it's 100 watts. What does it mean? Well, it means 100 joules per second consumption. It means every second there's 100 joules of energy is consumed by that light bulb, okay, or dissipated by that light bulb or generated by that light bulb, okay? So that's why 120 watt light bulb is brighter than 60 watt light bulb because 120 generates 120 joules each second and it's radiated away. So we have kind of two equations. Here's the equation 1, which is amount of work done per time, which technically here's like, let's say, can also be represented as change in energy over time or amount of energy over time, right? So, but you can also calculate that by taking the you can see, right? For example, if I take power, which is work done over time. Remember, work done is nothing but force times displacement over time. But see, if I take displacement over time, well, displacement over time is just velocity, right? That means it's force times velocity. That's where we get that second equation. So equation 1, in terms of energy per unit time, or equation 2, force times velocity. So that's why we have two equations, right, for power. All right, so I have one last example, from this chapter, which, allows you to see how the power can be, incorporated into this type of calculations. All right, so you have a 1,500 kilogram car is behind a truck traveling at 60 miles per hour, which is 27 meters per second. And to pass the truck, you speed up to 75 miles per hour, which is 34 meters per second, in 6 seconds. What engine power is required to do that? Right? So because to speed up, your engines have to do work to increase your kinetic energy, right? All right, so given the mass of the car, what you're told here, let's say here's your car, let's say this is position 1, so it moves to this position 2 in order to pass the truck, okay? And it happens during this 6 seconds time interval. So at position 1, we are moving at 27 meters per second. At position 2, we are moving at 34 meters per second. And we're also given the mass of the car as 1,500 kilogram. All right, so given mass and speed, one thing I can do here is do this, right? I can calculate, okay, so what was kinetic energy at point 1? Well, it's 1/2 mass times speed 1 squared. What is the kinetic energy at point 2? Well, it's 1/2 mass times speed 2 squared, right? So I can, in a way, calculate that. So plug in mass and speed at position 1. And here's the thing. We're going to calculate this as 5.47 times 10 to the 5 joules. And if I calculate kinetic energy at 2, I'm going to get 8.67 times 10 to the 5 joules. And you can see, right, I have to get higher K2 because, we're moving faster at point 2. All right, so that means I can calculate my delta K because I have K2 and K1. Well, this is equals to K2 minus K1. And if I do the difference of those two, we're going to get 3.2 times 10 to the 5 joules, which is the difference between kinetic energy at point 2 and kinetic energy at point 1. Well, remember, what is delta K equals to? Well, delta K is equal to the work done, right? That means work done by your engines is also equals to 3.2 times 10 to the 5 joules, because that's how much your kinetic energy changed. Well, then one thing I can do here is I can calculate the power, which is then amount of work done per unit time, which is then 3.2 times 10 to the 5 joules during the 6 second time interval, right? And if we do that, we're going to get 53,000 joules per second, which then can be written as 53 kilowatts, right? And that will be then in terms of the amount of work done per unit time, which is the power of the engines. That means, 53,000 joules each second, or, it's generated by your engine to allow you to speed up from 27 meters per second to 34 meters per second. All right, guys, so this concludes chapter 7, which was on conservation of energy and work done. So basically anything energy related, right? So make sure to, once you watch this video, we're going to do discussion, and then we're going to do, make sure to do the homework problems, right? And try to use all those examples as a reference, right? To do the, the examples on the homework.